Hi, my name is Elizabeth Haney, and today I'll be presenting my implementation of a trie-based search autocomplete system for this project. This project simulates Google's search functionality using custom C++ data structures. For the next 10 minutes, I'll walk you through the design, implementation, key algorithms that make this system work. This project consists of four main parts, each building upon the previous one. First, I constructed a custom trie data structure. This will be the foundation that stores our dictionary. Second, I implemented an autocomplete feature, which allows the user to enter a query and then suggest autocomplete options, kind of like Google. And finally, we implement an algorithm to suggest the top three most similar queries for the user if their query is not found. Before diving into the implementation, let's first understand what a trie is. A trie is a specialized tree that is used for storing strings efficiently. Each node represents a single character, and each node has paths that lead to different possible words. So each node represents a single character, and paths from the root to any node represent prefixes of stored words. The key advantage is that words sharing common prefixes share the same path, which makes it extremely efficient for autocomplete functionality. So notice how Bear and Bell in the diagram in front of you both start with B and E. So we start at the top of at the root node, and then we start with the first character, which is B. And then after B, we have E. Say the input is Bear. So we go down the structure B, E, then to A, and then to R, and it terminates there in the end of word. So the trie node class is the building block of our trie. Each node contains two key components, a children array that holds pointers to 26 possible next characters. Each one of those pointers is representing a letter of the alphabet. And also we have in this class an end of word Boolean flag, which indicates that we have arrived at the end of a word. And this will be important for determining the autocomplete options, because we will traverse down the tree from the word where we started with our query all the way down through the tree and hitting all of the end of word nodes and then returning those. So the end of word Boolean flag indicates whether the node represents the end of a valid word. As I said, the children are initialized to null pointer, and then we use end of word flag to distinguish between intermediate nodes and actual word endings. For example, if you were to have the word T, the node at A would be the node that has end of word set to true. The trie class is what manages the trie nodes. So the trie class manages the entire structure through a root node pointer and provides essential methods for building and accessing the tree. The insert method is very crucial here. So it starts at the root and traverses down, creating new nodes as needed. So for example, if we have the word cat, we would start by creating the C node, which would go into the children of the root node at the position of C in the alphabet. And then we would go on and then insert A. So A would be a child of the root node C, and then T would be a child of the node A. So traversing all the way down to T is the end of node character. And convert character to num is one of the methods here that helps us with this. So convert character to num converts an ASCII character to a number or an integer. And this just makes everything more efficient, as we really don't have to worry about dealing with actual characters. We just use indices for alphabetical letters and for our children array. The initialize alphabet method is what sets up our character mapping for the alphabet. So that's just an example of how we would add a word to the trie. The autocomplete feature allows the user to enter a word and then provides options for how it can be completed. In this example, we see the person has entered the word hack, and from that, they could possibly be typing hacker, hack it, hacking, hackman, hackney. And the way that this algorithm figures it out is it arrives at the end of the word with K, and then from HAC to K, it sees what node and what children fall below hack, and the children that fall below hack, it could go next to E, it could go next to I, next to M, and that's generally how it works. The search class is where the autocomplete and recommendation search algorithms live. It ties those all together in the same class. So the autocomplete method serves as the main entry point, accepting a user query, and it returns a list of suggestions, as I mentioned before. It calls find matches, which is what does the heavy lifting of traversing through the tree and using regression to find all of the possible words that the user could be typing. And finally, we do have the recommendation search, which I will touch on in a few seconds. And all of the predictions for the autocomplete get returned as a predictions, which is a vector that contains strings. Now we get to the really fun part, which is how the recommendation algorithm works. The recommendation algorithm allows a user to search for a term, and then if it can't find that term, then it will suggest three strings or queries that are very similar to what the user typed. And I've chosen to use the Radcliffe-Ober's-Help algorithm. So this algorithm calculates string similarities by finding the longest common substring. Then it recursively examines the unmatched regions on both sides. If the similarity score is actually calculated as twice the number of matching characters divided by the total characters in the string. So looking at the example that I've given, cat and hat, the longest common substring is AT with 2 characters. So the total characters is 6. So the similarity equals 2 times 2 divided by 6, which gives us 0.667, or about 67% similarity. So these words are somewhat similar. The recommendation system activates when a user's query doesn't exist in our trie. So the recommendation search method compares the user's input against every word in our dictionary using the Radcliffe-Ober's-Help algorithm. While other systems might use Levenshtein distance, and I think that's usually what's taught in computer science classes, I think this is actually a better method in our case. So the Levenshtein distance counts the minimum number of single character edits needed to change one word into another. Our implementation uses Radcliffe-Ober's-Help because it focuses on shared substrings rather than the individual character changes. For example, Levenshtein distance would say Hopper and Hope are distance 1 apart, but the Radcliffe-Ober's-Help gives us a similarity percentage based on how much of the original characters are actually preserved. So our system calculates similarity scores for all dictionary entries and then sorts them by score and returns the top 3 most similar matches. This provides our users with helpful alternatives when they make typos or search for terms that don't exist. So the system is intelligent to suggest hope when someone types HOPR, making it possibly more user-friendly than the Levenshtein distance algorithm. And finally, I just want to show the demo results. So we can see, like in the assignment in our project, we were asked to do a autocomplete for binary and then the substring SEA. And unfortunately, my algorithm is not able to handle multiple terms, and I wasn't able to accomplish that with this project at this time. But as you can see, if you type in a word like hack, you'll get HACK, hackett, hacking, hackman, and hackney, which I think demonstrates that this does a pretty effective job of autocompleting. And then when it comes to recommendation results, when we can't find a term, you can see that if you type HOPR, which is not a word, you'll get HOR, HOP, and HOOPR, which are in the dictionary. And these could be Yeah, these could be alternatives, or maybe something that you're trying to type, but just didn't type correctly. So yeah, and then another one is the word trendy. So trendy is not a word in the dictionary, in this dictionary at least. So instead, it's recommending trend, tray, and tend, which are all still quite similar. Thank you for listening to this presentation. Hope that, well, you as a teacher probably didn't learn that much, but hope you appreciated this presentation and have a great rest of your day.